Okay, so finally we're going to look at degenerate perturbation theory, which is the version of perturbation theory where you can actually deal with the fact where you have degenerate eigenvalues. In other words, where the energies are the same. So what if, so obviously if n equals m, these two are equal, and therefore we get 0 on the bottom line, except the case where they're equal is explicitly excluded from the sum here. When they're equal when m is not equal to m, you'd be dividing by 0, and dividing by 0, of course, destroys the universe. But of course, it only destroys the universe when it's a physical quantity, and in order to generate this, what we did was we divided by this on both sides. And so if we go back to our derivation, when we have this condition, we can't divide by this difference, and in fact we have to deal with those terms in a different way. And in fact, those terms wouldn't come up at all if the right-hand side was 0 as well. So these terms here, if they are 0, then these terms don't come up, so we don't have to do any dividing. We just ignore it from the sum entirely. But can we actually have any control over whether those terms are 0 or not? This is the off-diagonal terms in an expansion, a matrix expansion of an operator, and that operator could be anything. Well, what we know is that these energies are the same. So actually we have some freedom here. So we know that H naught acting on one of these states, let's call it psi A, gives us some energy. And we also know that when it's acting on some other state, some linearly independent state, that we get exactly the same energy. And it doesn't take much to convince you that if you take an arbitrary linear superposition of these two, the H naught acts on each of them and brings out an E. So in other words, we have some subspace that all have the same eigenvalues, same energy eigenvalues, but in fact we can put that subspace into any basis we like. Any linear combination of vectors inside that subspace is an eigenstate. And so we've got complete freedom within that. And how strong is that freedom? Well, remember, this operator V is a Hermitian matrix. It's a Hamiltonian term. And so it actually can be diagonalized. And it's Hermitian in its full Hilbert space, and therefore it's also Hermitian in some subspace. And so we have some arbitrary, let's say we have 3 of these things. So we can write a matrix version of this, which would be where each of these terms, so we have a matrix like that, that's always diagonalizable. So there's always a basis you can choose within this subspace where you can get this, with all the other terms 0. And that's the whole problem. So if you can do that, then what you end up with is that this equals 0 for I not equal to j within this subspace. And if that's 0 for I not equal to j, then you don't have to worry about those terms at all. So what you end up with is a variant of this problem. Then you get a variant of this equation, which is almost the same. And what you end up with is you deliberately exclude all the cases where the energies are the same, rather than just where the indices are the same. And so that's what you get with your degenerate perturbation theory. So the whole trick, of course, is to do this diagonalization. That can in general be quite a hard and messy thing, but what you're really doing is you're finding a simultaneous eigenstate within that subspace, where the eigenstate of your unperturbed Hamiltonian is also an eigenstate of your perturbation. And by looking at the structure of your perturbation and thinking about that, maybe the symmetries of it, you can often have a pretty good guess on exactly what basis to choose. This doesn't come up in non-degenerate perturbation theory because you don't have any freedoms. You don't have the freedom to choose your basis. You're fixed to have the basis of your unperturbed Hamiltonian. And if you recall, the formula for the second order energy shift came straight from the formula from the first order state change. And in fact, you always need to know the states for the previous order to get the energies for the next order. And therefore, if you want to get the second order energy shift, it works exactly the same way. You have the same formula as we have here, except instead of having the indices having to be different, you just have the energies having to be different, provided you've managed to put yourself into the basis where your interaction Hamiltonian is diagonal. And that's basically what we wanted to cover in the quantum mechanics section of this course. We started off by recovering the basics of quantum mechanics, the fundamental axioms. Then we went on and we talked about symmetries and transformations and looked at conserved quantities, just like we did in classical mechanics. We also looked at the Lagrangian formulation of quantum mechanics and how the principle of least action from classical mechanics is actually emergent from that. And we also went on and looked at these calculational techniques fairly rapidly. There's not that much more to cover in terms of showing you them. What really has to happen now is you have to have a go. You have to try them. And so we'll be doing that in assignments and in exams and in practice for exams and things like that. Our next topic is going to be relativity.